So in this problem, we are trying to find the rectangle's dimensions that would give us the maximum area. And this rectangle is bound by the x-axis, the curve y equals the square root of x, and x equals 9. So the height of this rectangle is defined by the square root of a. It's the height of the curve at a. And the other dimension is the distance 9 minus a. And so we're trying to find the maximum possible area, which requires us to find an equation that relates to area. So the area is length times width. And in this case, I've already gotten the length and the width in terms of the same variable. So it's the product of the square root of a times 9 minus a. So I'm going to do a little bit of algebra here. And I'm going to distribute, as well as I'm going to turn my radicals into exponents. So that way when I take the derivative, it's a little bit easier. So to maximize this, we are going to take the derivative of the area function. And that gives us 9 times 1/2 times a to the negative 1/2 minus 3/2 a to the positive 1/2 power. And we'll set that equal to 0. And let's go ahead and simplify a little bit. So that gives us 9 halves times 1 over the square root of a. I'm going to put it back into its radical format. Times the minus 3/2 times the square root of a. And that's equal to 0. And I'm going to go ahead and get rid of the square root of a in the denominator. And I'll do that by multiplying through by the square root of a. Let's go ahead and distribute here. If we do that, that gives us 9 halves, and the square root of a is cancel, minus 3/2, and square root of a times the square root of a is equal to a. So that's equal to 0. And then I'm just going to isolate a by bringing it over to the other side, and then I'm going to get rid of its coefficient by multiplying both sides by 2, and then dividing both sides by 3. You can also get this same result by multiplying both sides by 2/3. So now, once we have that information, I'm going to test to make sure that we are getting the maximum area. And so I'm going to use, instead of the first derivative test, I'm going to use the second derivative test here. So I'm going to take the second derivative, which would give us 9 halves times negative 1/2 a to the negative 3/2, minus 3/2 times 1/2 a to the negative 1/2. And what I'll do is I'm going to test my second derivative at a equals 3. And it will tell me whether or not my function was concave up or concave down, and thereby letting me know whether this would give me a max or a minimum value. So first I'm going to do a little bit of simplification here. I'm going to turn those back into radicals. And let's go ahead and find a double prime at 3. And when I do that, it gives me negative 9/4 times 1 over the square root of 3 squared, cubed, minus 3/4 times 1 over the square root of 3. And if you have a minus, a negative minus another negative is going to give us a larger negative value, so therefore the second derivative is less than 0, which means my function is concave down, hence that critical point is going to be a maximum. Now once I know that dimension, then I just need to find my other dimension. So going back to our graph here, that's 3, that's is 9, draw my rectangle, which means that my one dimension is 6, and then the other dimension is going to be the square root of 3. So A is the x-coordinate, that would give me that max area. And those are the dimensions.